Hello and good evening, everybody. A little late coming in on this, I think, because it's uploading a little late, but that should be fine. So what we're doing today is we're going to be talking about space traffic management again, like we did in the first class, or like I did in the first class. And I will be talking about this time, the little bit different, as I delved deeper into the AI aspect of the data fusion system. To put this in simple terms, there, once again, are the only people that are controlling the satellites that are in orbit right now are people down here at the ground. So they're using something that's called telemetry, T triangle. It basically what happens is we send the radar up, it hits where the satellite is going around the Earth, and then it just comes right back down. And then another satellite catches that, and it can, judge by the hypotenuse where it is about. And a lot of what I'll be talking about here today is going to be dealing with common filters and a lot of these measurements for predicting where a satellite is because, they're far away. It's not instant with them. It can be, but they're moving really quickly and they are a lot farther away. So we really want to get rid of the noise and find out what it is that actually does predict a satellite's position in orbit very accurately. So that's what I'm doing here today, and I hope you guys enjoy. All right. First, I would want to talk about the picture here that I found. So it says 57,000 satellites planned through 2029. That is from a Business Insider article that had just come out a couple months ago, I believe, if I remember correctly. I'll put the link with the PowerPoint. However, this is seemed almost impossible not too long ago. But as I'm sure most people, unless you're living under a rock, really, has heard of Elon Musk, and they know what SpaceX is, and they know what the satellites are doing. Or, sorry, not what they're doing. They know what Starlink is doing with the satellites. And this is an accurate representation of different companies. So the green, I believe, was Amazon, and then the one with all the pink clusters, that was Starlink, who definitely has the most. We have over, since I did this last, I wanted to make this point. We had just hit 11,000 back in August, satellites in orbit. 11,000. Now we are up to almost 15,000 in just that short of time. And it's going to be growing exponentially. They've been launching every other day. I think they already broke the record for launches for satellites, like all time. Then they did it just within the year. And that is why this is very important. Once again, it's getting ahead. It's getting ahead of the problems right now. It's not like you can be down here on Earth and with stoplights and stuff up there. Uh, which brings me to my other point. Little less technical one is that a lot of people get very confused about the how much traffic is in space. Like how much is 15,000 satellites to low Earth orbit going around it? Well, it's really nothing right now. And the best example that I could give you to make this, really, really sink in your head, just think about being, I'm here in Orlando, for Full Sail, and there's 2.4 million people in the Orlando metro. Okay. I think the city limits is like just below 300,000. And that is in a lot smaller area than the entire low Earth orbit. Like we're talking way bigger than the equator because it's up, like, I forget how many miles it's in the air. And that means there's a lot of room. But the problem is that we're going to be taking that up exponentially faster here very, very soon. It's not like an automobile boom, but that was, I think, the best analogy I could give to somebody not really nerding out about satellites. So that's really why I'm doing this. That's what I'm looking to do. All right. And yes, so I guess I got a little bit ahead of myself. And so this does lead into why AI is important. Like I said, with all these satellites predicted to 59,000, it's already very difficult to manage just sub 15,000. And that we're doing everything we can. They are very short-staffed. I know some people that are working there. I know some people working at other companies trying to compete with them, and they're understaffed and they're trying to poach. It's a very big industry right now, and I do know for a fact that Elon Musk just brought up to his GNC team for Starlink and Starshield, which is the military version of it, that AI will be absolutely being implemented here soon into their space or objects or craft, whether it be in orbit for exploration, regardless of what it is. But for now, we're just going to talk about the satellites. So that's the first time it's ever been mentioned at SpaceX, which I have to say I'm a little happy about. I feel like I stumbled upon something here that not many people are thinking about. But it's just I just really like space. Really like space. I mean, just look at this picture of the orbits here. There's a whole bunch of different kinds, and they're all used for different reasons. Like geosynchronous is really, really, really good for TV broadcasting. And then GPS satellites are in medium, so they are always equatorial, so they can get the most surface of the Earth. And they're very interesting, and they're starting to blow up right now, and that is actually what the problem is. So, and right here, so how do you gather information from a satellite, right? It's called a TLE, which stands for a two-line element. And I have that here. If you can see my mouse, it is the notepad picture that I put up that's highlighted. And all there are two columns here. So, you have GOES, and then you have one and two lines. All of these each represent something different, and that is what this picture up above it is showing you. And I thought this was really interesting because I kind of just forgot once you're in the trenches, always looking at these like documents that I'm trying to feed into the module and get it to read it. And maybe that data is not good. Sometimes you get a bad batch from Celestrack, which is the site that you get it from, celesttrack.org. Oh, whoops. And I just had forgot that I was just using TLE like I'd been doing it for years, but it's a very interesting and kind of complicated system that they have that they just mashed. The government was trying to be real efficient and smash them all in to very small text files so that you don't lose data. Um, but yeah, so you can see here that it tells you the satellites numbers, it tells you the inclination, all this stuff. It's kind of a lot of jargon, but these are the measurements that I'm trying to read in my Kalman filter, which takes a bunch of these things together. I'm getting a little ahead of myself, but it takes a lot of it together, and that is how a satellite can predict where it will be at its next point in its orbit, which would help us to know if another one was going to be there. And these are insanely important. They're pretty much the whole part of my project is trying to figure out the best ones to read in, which one of these factors in more. Like, what is my batch? What is my epoch? Like, for each one, so there's a lot that you don't want to do too much on or be too specific because not much, there's not much noise in the data because it's just by itself in space. Um, but yes, so once again, it's pre-processed with machine learning. And here we go into the Kalman filter, and let's go to the picture first again. I like doing that better. And what you can see here is this is a perfect prime example of a Kalman filter. It has these like a Venn diagram is essentially what it is. So you have your odometer of, how fast are you going? What is your speed, not your velocity. And then an IMU, IMU takes the constellation and coordinates of Earth, and then it takes that and like it knows where it's at by looking at constellations and stars are always going to be there. I'm trying to put it in an easier way, but it kind of sounds absurd, but we've been doing it since the 70s. It's kind of how our missiles work too. They're able to, and they're also able to use a gyroscope to kind of calibrate it too, is what an IMU does for sure. Um, but then it also has a GPS on it. And all of these things are trying to estimate its exact position. So let's kind of break that down a little bit. I know this is a lot, don't want to get too deep into it. However, using the GPS, so think about this. GPS is in a different orbit. If we go back to the slide, GPS is in medium Earth orbit. So let's think about this in terms of military. That's in a completely different than low Earth orbit where the ISS is, the Hubble, pretty much like all of our weather satellites, like for the most part. Uh, but then there's not many phone companies down there. But then the phone companies are a little higher. And then you have geosynchronous for data, like so you can just sit over one area of a country. And that's on a completely different level as well. And so are the weather satellites. And on top of that, um, there's Sirius radio, which could be important in times of war. But the point is that they were very intelligent when coming up with this Kalman filter. And this is another very big piece. It doesn't seem like it, but if one of these fails on a satellite, the other two will make up for it. And that's the whole entire point of a Kalman filter is that we want to take in the most amount of different, I want to pull from here, from B, from C, from D, and then I want to put it all into F. And it's like, okay, but what if A breaks? Well, that's fine because then B, C, and D and E will work. And it's you're basically just optimizing accuracy is what this is doing. And it essentially makes predictions on itself based off of its own past data, which is also very, very efficient. Um, and a very, very good invention that what this Kalman filter is. And then so the module that I learned was the short-term module. I'm sorry, the long short-term module, which essentially is a type of RNN, and that's a recurrent neural network. And there's a problem with these RNNs. I think yes. So you can see it right here. They regularly face a vanishing gradient problem. Um, and this can actually prevent that by using sequential data and learning on itself. That's a little broad, but to be a little more specific, how that would work is if it's, how do I want to put this? Sorry about this. Essentially, it's like a very human way to do something. It's like, okay, I did A, and I can still remember I did A last week, but that led to B, but I wanted to get to C. So I know I can get to C. So it's a deep learning model learning off of itself by using the most accurate points and or using the least amount of error points, I guess is the best way to put it. So if there's an 8% error over a 9% error, it's going to take the 8. And then, well, I'll show you here in the code for a second. It might make a little more sense. I think this is getting confusing a little bit. Um, but I'll show you this slide and then I'll go to my code. And then I want to come back to that. I didn't explain that well yet. And, but let's get in. So the error and computation model improvement, this was probably the most difficult part of the code for me because it's really the only deep learning module part I did. The rest of it was more about reading in data, understanding how I wanted to plot it, 3D, integrated, twisting, interactive. But this is actually what was giving me what I was looking for. How accurate can the model that I came up with predict these mock data points that are just out of random? I RNG'd it, random number generator. But so, and I use the Euclidean distance. So these units are essentially like with Earth, they're sized down. I forget the exact calibration, but for instance, prediction zero you see here is 112.78 units. That means this orange dot or these orange X's was that many units or Euclidean distances away on this globe from the purple dot, which was a real mock satellite data. Um, and it originally I had it set so the module how it works is you choose the percentage that you want it to take in terms of what is the best or the least amount of error. So originally I had it at 25%. So the best 25%, the lowest 25% errors, or the closest to the purple dot is the best way to put it. But that didn't give me, it really didn't give me enough data. I also raised the batch sizes and everything, and it really just it was when sorry about that. It was when sorry, I just lost my train of thought. Wow. It was when I changed it to 10%. Yes, because I was at 25%. And when I changed it to 10%, I started to get a lot better data, and I noticed it starting to learn on itself after just, a couple of run throughs. Um, so let's go ahead and get into the code here. One second. Let's pause my sharing. I think I'm sharing my screen. Yes. Okay. Perfect. Awesome. Thanks for sticking with me there. That was, sorry, I was just really thinking about all that. All right. So the library is being read in. This is how I'm fetching the TLE, remember? That little two text file, two row. This TLE data from celesttrack.org. And you just kind of put it in here. And on top of that, it has an actual read-in file or a read-in function within Python where you can just it's just built into it. So they openly give this to us. Now, the problem where I ran into all of this uh, was getting that data because the way I have it all set up right here was how you divide it. Um, but the worst or the issue was that Celestrak only allows 2 to 3 data pools from their satellite networks every 2 hours. So if you data hog, as they specifically call it, they will ban you for 2 hours. And if you do it again right afterwards, because I found that out because I didn't actually know why my code wasn't working. Um, and it happened to be because they had banned me for 4 hours. So I had to go and rewrite some mock data. So my code's a little different, I guess. I kind of just had like one for the mock and I had one for the real. But whenever it can read in the real, it works. But this is how it will work. It goes through the epochs here. It's showing the loss. It's showing how fast it took to do it. Its progression. Here are the units. As you can see, they're a lot lower than that picture I took. Uh, there's a couple way up in the hundred, and I only see these two at first were, but it's not as varied. And that was what I started to notice as well, which I really enjoyed. Like you get a couple of these like on 78, 104. Um, but these orange X's are getting much closer to the purple dots, and that's I'm very happy with that, very proud of myself for it. And it's just exciting to see it all come together because it took a lot to get to even this point. So yes, and so I did put that I did want to make a point that I did see a reduction in error over multiple cycles. And I think we actually just in comparison to that photo and mine, I'm almost positive that it's the same. Or there was a big jump. And so here are the challenges. Yeah, the real-time satellite data from Celestrak into IO and AMSAT. AMSAT actually was able to give me some mock data it helped with, but yeah, there's two sites there. I guess they have a deal with the government, and the government obviously doesn't want to have people just spamming their satellite data. That's probably a security risk, which is another big issue with satellites. Um, in the prediction accuracy across different regions, yes. There was when the satellites are not over like an American territory or a ally of ours, I tend to notice that it just jumps off. Like you just don't really get a good reading. I don't think we're actually getting the readings, or if we are, they're not. For somebody like us in the public, it's somebody's got to have a clearance for them. So it is difficult because I'm constantly having to go on Reddit or Google to find somebody coming up with mock data that they've been doing with this already. But it would be nice to be able to work with the real data, which doesn't happen often. Like it happens maybe once a day. So the LSTM module, I noticed too, like I said, with the batch sizes and stuff like that, it was very finicky. If I put it, I don't want to get too technical, but if I half the size, it would be very inaccurate. But if I doubled it, it would also be very inaccurate. And it was a very fine line of fine tuning between that. Uh, but it did do, I am expanding it to do continuous updates. But like I said, that I had to get approved from Celestrak, so I'm still waiting on them to respond back to me. You need an approval. It can give it to me every 10 minutes. It can give me an update. All right. And the takeaway, uh, yes. So the key achievements, like I said, I had already mentioned both of these, that I actually was tracking things in real time. That was getting closer, and I would say this is probably my first actual deep learning module where I made it from start to scratch myself, not for somebody else, something I wanted to do. And it worked out. It really did. And so I'm very excited about where this could be going because I'm a little bit further than I thought I would be. Um, and once again, the impacts on space traffic management, I will bring up again. My brother works for Starshield, and his job is actually just he's a GNC engineer, and he deals with keeping the satellites up. He doesn't write the code or deal with AI or anything, but he's been telling me that there was very, very, very there were some very close calls just recently, and very close. And he was very worried, and so was Elon and the government. And that's why this is a big deal because it's not that big of a deal until it happens. And now you have space debris, and it's flying at 17,000 miles per hour plus. About 17,500 is what you need to be into orbit. And any piece of metal flying at that with no air resistance, it's just a tunnel and it's going to break through everything. And it could just take down already our infrastructure that we have up there. And that is what I believe is the most important part of the space traffic management. It's not necessarily just the AI. It's that the AI absolutely can fix this or solve the problem that is inevitable. But the actual problem is that it is very much a big deal to everybody, from using your phone to anything, your car, to finding out where you need to go, your GPS, TV, just even satellite TV, cable TV, all of it. You need satellites. So I'm hoping that it's starting to catch on. Once again, like I said, Elon had talked about it there at his meeting just a week ago. And I know that Jeff Bezos has been talking about it, but hasn't actually brought it up. So we'll see. I know OpenAI has been working with Stargate, and a lot of money is being thrown into space with AI. And I'm very excited about seeing where this goes. I'm very excited about seeing how the space industry and the computer science industry merges again. Thank you for watching. My name is Corbin Zatt, and I have one more slide here. There's my full sale email if you want to get in touch with me. And everybody have a great night.